Australia, big, empty, a long way from anywhere. It's the perfect place to automate. There are so many applications in Australia where you can apply robotics in mining, in materials handling, in agriculture, in marine environments, for defence, for bushfire fighting, you name it. If you wanted to do automation, Australia is the place that you'd come and do it. And in fact, in the last 15 years, Australia has gone from not too much to probably being one of the leading developers and users of robotics. And I think that often comes as a surprise to people. And some of that really is the reason that there are just so many good applications for this kind of technology in this sort of environment. So I'm going to tell you a story about how we got to this point. And I'm going to go back 20 years and show you, starting out, one of my very first robotics projects. And this was a pretty important project because it was one of the very first robots that went around with sensors, mapping the environment, trying to use that map to do navigation. It integrated planning, it integrated control. It did the sorts of things that you would like a mobile robot to do. And it was an important developer in a number of different ways. And we'll see this particular project impacting so many of the things that I've done, in fact, in the last 15 years as we go along. And it was interesting also, because we'll close the loop at the end, that actually one of the very early applications of this sort of technology was indeed in assisted care environments. So this was one of the challenges that we posed for ourselves at that time. So some of the technology from this went in fact, originally into developing AGVs for factory automation. So we worked at that point with Caterpillar, based in Rugby, to develop laser guidance systems for free-ranging AGVs that move components around a factory. And there were a lot of interesting lessons in there in terms of how you go about commercializing these sorts of things, the core technologies, navigation, control, guidance, systems engineering, and so on. But as I was doing this, I met an ex-army colonel in the UK, and he'd been actually commissioned to design a new container terminal. In fact, this is it when it's fully populated. And interestingly, he'd been asked to basically design the terminal so that it could be automated. No one had actually developed the automation for this sort of thing yet, but nevertheless, he was given the task of thinking about what you would do. And you'll see here, for example, there are rail-mounted gantries and things that basically attempt to make it easy to do this thing. And surprisingly, he and I actually got on extremely well. And we looked at this problem, and I basically said, well, how hard can it be? I mean, it's the simplest possible robotics application in some sense, because all you've really got to do is to pick up boxes and move them around, right? There is an issue, of course, of scale. So you're not moving around little boxes, they're big boxes. Speed, integrity, there's how you actually integrate it as part of an overall container terminal, things like that that basically go on. But nevertheless, we got together, he got the money, and I got the technology. So I sat at my kitchen table, figured out, well, how do you build a very large AGV that can go at high speed? Problems to do with sensing outdoors. How do you see through rain and things like that? So development of things like millimetric band radar sensors. How you actually worry about safety. So you can never have one of these things running over someone. These are big vehicles. And at the commercial side, also, how do you actually go about developing some of these? These are capital-intensive things. You've really got to involve not just the terminal operator, but people who actually develop equipment, how you go about investing and so on. So to cut a long story short, over a period of about 2 or 3 years, we developed this vehicle here, probably at the time one of the largest, fastest AGVs there were. It involved a huge amount of innovative research, and in fact I would be fair to say that if I'd done this as a research project, this would have been absolutely wow. It is only in a commercial sense that you get really forced to think about these things. So as I said, development of things like millimeter wave radar, interesting things here about how you actually model and control platforms like this, because as a load comes down, as you'll see in a minute, the entire platform deflects. So it's not a simple thing like you have an AGV in a factory. You've got to worry about things like tire radius changes, uneven ground, all these types of things. Real-time systems. Remember, this is 20 years ago. So getting computers to do all this processing and control at that time was a non-trivial thing. And how you actually go about integrating it, not just as a standalone AGV, but into the rest of the thing. There are a lot of commercial hurdles, and for me this was also an extremely valuable lesson about how you get the user to accept technology like this when they've never seen a robot before. How do you actually make a commercial case out of something like this? Is it cheaper just to have a driver or something like that? And also about issues of how you invest in these things. I think even more important about this project was all the failures that we made as we went along, because I think you learn a lot more from failing with something than you ever do by having a success. So some of you may know, I don't actually drive. I've never had a driving license. And you'll notice this vehicle is actually going in reverse at this point. And I had this algorithmic idea that, well, if you were going backwards in a car, surely if you want to turn left, you'd turn the steering wheel right. Okay? And I wrote the code to basically do that. And at this point, my colleague, who was also working on the project, realizes that actually I don't know how to drive. And there is a ripcord on the side here. And he's just about figured out at this point that the vehicle is not going to do what it said. So you learn from that process. And we did learn. We learned a lot about, for example, designing systems so that they actually work first time, every time. I also learned a great deal about commercial element of this end-user support, the need for support, and the fact that basically people are not going to invest in a startup company that's run by a bunch of academics, at least not at this scale. Okay? And it was a very valuable process in doing this. So by this point, I was no way I was going to work on indoor robotics anymore. It was much too much fun working on these large things. And again, if you live in Melbourne or you live in the UK, you don't want to work outdoors. So I decided to move to Sydney to continue this. So the field robotics bug was really big now. I thought big vehicles, big applications, if you like, the IBM 370 of the robotics world. We really were able to push the case in these areas. So I looked at what was out here, mining, agriculture, marine environments, and I thought this was the place to be. And there were nice pictures of beaches and things like that, and nice pictures of mines, which I thought I could automate. And there was also a job going at the University of Sydney, which was a pretty important part of it. Very enthusiastic people, good support, and surprisingly, in my view, very good funding in Australia. Much better funding for this sort of research probably than anywhere else in the world. And because the university were pretty naive and didn't know what I was doing, there was plenty of freedom as well to get on and do this kind of project. So, as fate would have it, at that time, Chris Corrigan had just bought Australian stevedores. And one of the alumni from our school, John Young, got in contact with me and said, well, what can you do in the container world? And in fact, we started out working on what they thought was the real bottleneck, which is the speed of cranes over ships. And we worked on new reeving systems, new control systems, and so on, which would actually speed up this process. And after we'd done this and built this large model, Chris Corrigan came to the lab and saw it and thought it was good and said, well, what else can you do? And I showed him a video of that freight vehicle, and he said to me, well, can you automate a straddle carrier? And I said, no problem. And so as it started at that point, we decided to go ahead. He was interested in investing to improve waterfront efficiency. They just bought these straddle carriers here. I have to say, these are pictures from when I first visited Patrick's 15 years ago. Bone age, archaic, would be an understatement for the way that Patrick's was at that point. So he bought us a straddle carrier. Here it is. They're quite big machines, 60 tons. And one of the great things about this is getting a second bite of the cherry. You've done it once. You've made all the mistakes. We had PhD students work on integrity and vehicle modeling and things like that. And we kind of knew some of the answers now. And to have someone come back and say, do it again, is one of those things that just never really happens except in a fantasy. So we got all the new research results we had, detailed vehicle model, high integrity navigation system architectures, provable levels of fault detection, all these things. We got the new straddle carrier, we had a great team, and more than that, because the CEO was involved, it was a long-term support. There was a recognition that this was not going to happen in 1 year. It was going to be more like 5 years or 10 years. And that's so important in these projects where really you are breaking this ground. And particularly also a flexible plan for how we were going to deploy it. It wasn't some idea that we were going to produce an X and then one day they were just going to put them all into the yard. There was a real thought process going on about how that actually happened. And at the time, if you remember, this is about 1997 now, we were having fun on the waterfront with the unions. Fairly well-known Minister of State these days, Greg Combet, said that what we were proposing to do was a fantasy, which is interesting in context of some of the things that he says now about robotics. But it was difficult. We had to work in a secret site somewhere in St Mary's, which is basically in Western Sydney and so on. And then gradually we started assembling the process. Again, the radar was very important to this because it was very important for doing all the navigation functions outdoors, collision detection and so on, integrated them into a complete system. And then around 2000, we gave our first demonstration of the system to the board at Patrick's. So this is, if you like, the first stage in a project like this. So we went on from there, and Chris Corrigan bought a new terminal for a couple $100 million in Brisbane, which he dedicated to automation. A number of people from the university team moved across to a new company. We looked at basically not just the whole process of how you automate a straddle carrier, the systems engineering and so on, but what happens with how you actually design an automated terminal. That is, actually worry about the safety, the interlocks, all the other processes that go on in that part. And that was a very important part of the partnership, where the industry person, actually who knew something about that domain, really helped you work that automation technology into the system that they were operating. And then in 2003, we ended up with a system with 5 straddle carriers on one terminal, Terminal 7 at Fisherman's Island, actually earning money off floating ships, shuffling containers, and this type of process. So it was a real major step. So a little later on, they took, again, a lot of people out of the university to help support this thing. They even hired professors occasionally to help them operate these things. Much higher pay working on the terminal than in academia. And finally, by 2005, we had 18 automated straddle carriers, and you'll see these are quite different. So they have no cabs, the drive systems are different, everything else. All the systems, the concepts are all integrated into here. And again, perhaps I'll emphasize a few things. You can never have a situation in which one of these things goes wrong, collides with something or whatever, because that would be the last time you'd be allowed to use automation. So it was very important here to get all those basic concepts operational. And it's grown now to 3 terminals up at the Port of Brisbane with about 35 straddle carriers. What's again interesting about this terminal, though there are operations people here, all the engineering that's associated with the automated straddle carriers, the operations and so on, is actually all run from Sydney. So it's all run remotely. Okay? So this is still, at this point, probably one of the most advanced commercially operational autonomous systems in operation anywhere in the world. And I also want you to reflect back a little bit on what perhaps the Patrick's terminals were like 15 years ago before we started this process. So there were a lot of important lessons in this project shared between both the company and the university involved. So I just want to say a little bit about the commercialization strategy, because I think this was an important lesson as well. In the earlier system that I showed you, the academics kind of owned everything, and it never worked. In this particular case, Patrick's basically owned the majority of what's going on. The academics and the remaining inventors own a little bit of what's going on, and the people who build the straddle carriers also own a sizable bit. And one of the lessons I learned from this process was that it's much better to own a little bit of something big than it is to own a large part of nothing. And I think that's a lesson that all academics need to learn, and indeed all universities, in fact. The commercialization strategy itself held a lot of lessons. So when we looked at what was going on here, there's probably about $150,000 worth of automation on each of the strads. But if you look at that, there's probably about 150 straddle carriers in Australia, so there's not much of a business, in some sense, building automation systems for these things. There's a lot more of a business selling automated straddle carriers, because they're $1.2 million each, right? So you can envisage, in fact, in principle, making a business out of this. But even better than that is actually not selling automated strads, but selling automated terminals. And this really helped us into a real recognition with what was going on with these things. Yes, there are savings with labor and things like that, but the real value in having an automated terminal or an automated straddle carrier is not that the straddle carrier itself is automated, but the fact that you vertically integrate it into the business. You change the business model. And that's the real benefit. So for the first time, these are savings here, but what the real savings come from is knowing where the straddle carriers will be all the time. Not just now, but 2 hours, 1 day in advance, and being able to plan and actually do something, change the way that you run your business. And that really was the main outcome for Patrick's. And I think it's a salutary lesson that in a lot of the applications we work in, it's the end users that actually benefit more than the people who actually produce the automation. So we've looked quite a bit at this, and I'll just point you down at the bottom here. Certainly there's a move now to move beyond integrated automation systems to provide perhaps automated terminals, and in principle, further into the future, perhaps even paper box type of operations. So there's another interesting outcome out of this. We had a startup company, Navtech, that came out of this, that developed the radars for the straddle carriers. They were a couple of my graduate students originally, and also, in fact, developed radars for other applications. And they've become an interestingly very, very successful company in a niche area, developing millimeter wave radar technology, 77, 94 gig technology, for things like debris detection on runways, counting traffic on motorways, security operations, and so on. And in fact, this year they won the Queen's Award for Enterprise. So this is another of these startups, which you'll see quite a few, that have come out of the lab that have made successes in interesting niche applications of automation. So one of the reasons I originally came to Australia was actually to work in mining. And there's a nice picture here. I love the Pilbara. It's kind of red and green, and it's got big holes in. It's a lovely place to work. It really is a grand challenge for robotics. It brings together all these different elements: perception, integrity, systems, and so on. And it's driven also, in principle, by a good model. There's safety, there's predictability, there's efficiency. There's all these things we saw in the container terminal in droves when you come to mining. And so when I first came to Australia, this is really what I wanted to work. And a lot of our early work, and there's a few people in the audience here, in fact, who'll remember some of our early work, we looked at basically that initial model we had. That is, let's automate an X. All right, so maybe we'll work on automated trucks. This is an example of using that radar for collision detection on a truck. Down here, there's a project that we were involved in, automating LHDs. But there was a real problem here, because the problem wasn't we need a robot. The problem was we need a better way of doing business. And I think at the time we didn't really understand that. So there was very much a lack of automation culture. I worked indeed with people like Andy Stokes, who are in the audience here, on key studies as to how you would actually catch the prize of automation. What does it actually do for the business? And so all of these sorts of things that we worked on at the time turned out really not to be successful at all, basic failures. And so we kind of refocused on looking, in fact, initially at least, at component technologies. And we worked with people like CRC Mining, another company that we started up out of the group, Accumine, which basically develops sensors which are some route towards automation. So, for example, this is the haul check system that Accumine produced, which basically gives you trucks guidance information. The trucks have still got people in them, but when the driver falls asleep, basically you know when he's going off the road, and it can warn him and everything else. Or radars, for example, that can image underground stopes or image from rope shovels. This is another system that Accumine produced, which is essentially a collision monitoring, collision warning system for large trucks and for haulier vehicles and various other things like that. So we had a large process of basically developing components for automation, because people just in some sense weren't ready for it or really couldn't understand, and indeed in many senses we couldn't explain what the benefit of automation was for mining at this point. And then things changed. At the height of the commodities boom, 2007, and I'd worked off and on with Rio Tinto over the whole process, there was a real thought that says what we really need to do is to talk about automated mining. Not automated trucks or automated drills or any automated X, but the whole process. How do you automate surface mining? And in many senses, the key to this problem is not so much let's build a robot, but it's worried about how you actually integrate everything together, how you worry about all the information that's in here and how you stick it all together, and only finally, let's take the person out of the cab. It's a lot more of a process-driven thing, very much in the lines of what I was showing you in the container terminal application. So the objectives in this case, and the program now has been running for getting on for 3 years, is really to take exactly those lessons, to improve safety, precision and efficiency, and in particular to vertically integrate the outcomes of that automation into the business. So the value is not in automating a particular component, it's propagating the benefit of that through the entire business, that precision, that efficiency, the information you now have, and so on. And in many senses, the same results apply. Who benefits from this? Ultimately, it's the end user, because that's what is becoming more efficient through that process. It's that systems integration with the user, it's the domain expertise, it's the information and so on. Of course, equipment manufacturers still have a significant role in this. You need to have automated equipment, drills, trucks, or whatever it is that needs to go into the mine, but you need to be able to integrate those things together to get that benefit. So the Rio Tinto Centre for Mining Automation has been a very interesting partnership. It's probably one of the largest investments by a company in a university group ever in Australia. And it basically is a good group because it has one mission: automate surface mining. All right? And if you like, it's not just about automating a particular component, it's about how all those things to work together. So the focus is very much on information systems, on how the whole thing gets integrated together, the research that's actually required to do that, the development process that pushes it through, and so on. So the university team has now grown to about 50 people, including graduate students. And the other real thing, lesson that we've learned, is it's not a one-year project. It's a 5-year or 10-year project, potentially even longer, to make sure that this whole process is followed through. And again, importantly, it's supported from the very top level, which is what really drives this thing along, a long-term investment for this. Equally, on the other side of the university team is a team from Rio, who take the stuff, okay, who really focus on how you're going to get the best use out of it, how we're going to implement it, how we're going to support it in the field. Now, a number of this team, in fact, they've all moved down to Melbourne this week, come from the university. So if you like, there's a process of handoff where we've got the research people, we've got the engineers at the university, and then as things mature, those people then take it both to Rio and to operate it in the field. So there's this whole virtuous process that's going on in here. So as I said, architecture, information and control are really what's going on in the main part of the center. So we worry a lot about how we're going to build a design and architecture which will support not just all the information systems that Rio use and all the new data fusion concepts, and I'll talk a little bit about those in a minute, but also, for example, how we plug in information from drill rigs, from different types of sensors and so on, and how we use the same architectural structure to plug into things that might be provided by another OEM, whether they be trucks or drills or explosives carriers or anything like that. And it's really a process of understanding how all that information, all those control attributes all come together. So there's been a lot of interesting work that's been going on here, and I'll just touch very briefly perhaps on one area. A big issue has been to actually use all the information that's generated in the mining process. So there's a lot of work that goes on, for example, using different types of sensors to build up real-time pictures for what's going on in the mine. Not just on the surface, but also under the surface, using, for example, drilling information that's obtained when you drill blast holes to come up with, in real time, estimates for what's going on in terms of the mineralogy, the surface structure, contaminants, things like that, so that you know what you're doing in terms of planning, efficiency, operations, this whole sort of thing. And again, I'll emphasize at this point, it wasn't a question of getting the man out of the loop. All right? It's really a question of how all these things come together to create a better product at the end of the day. And also at the surface of the thing, in this case integrating hyperspectral information with laser information and visual information to give you some real-time determination as where the good ore is, where the less good ore is, and so on and so forth, so that perhaps you can use that to control what's going on at the face in terms of loading and so forth. So capturing the prize, let's come back to the original thing. I think what's been interesting about the Rio Centre is to really understand that it's the end user. I think this is very important in an Australian context as well, because we have so many end users, okay, is that the technology that the end user controls, ultimately they're the people that benefit from it. So in this case, Rio controls all these enabling technologies, the information technologies, the data fusion technologies, and so on, and has a strong process of integrating that vertically into the whole way the business is run, the whole way that you actually do mining. And also, in addition to that, then using that leverage to try and encourage additional OEM engagement. And from that, developing the commercial outcomes. This remote operations centre that's been a little bit about it in the press. So this is a place at Perth Airport where now a lot of the mines in the Pilbara, a lot of their components in the mine are all operated remotely, the autonomous drills, the architecture for the integrated mine, and so on. It's a really exciting time, I've got to be honest here. There's a real transformation in mining coming, perhaps one that doesn't happen more than once in every 50 years. And it'll make not just a difference to what's going on in these particular mines, but it will make a major difference to the way that the economy works in Australia. So let me kind of go back to the beginning. You're beginning to see this story of a lot of different threads that are all coming back to the same sort of thing. And I'll go back to this robot here. You'll notice it looks very boxy. Okay? And that's because it was kind of designed to be modular. We built a lot of these different modules with sensors in, with controllers in, with different types of functions, and then we developed algorithms that allowed us then to build robots out of modular components. And every one of these boxes has got a computer in it, and there is no central computer in here. It's all basically just networked together. They exchange information using some fairly clever algorithms, and they use that to basically fuse information to decide how they're going to do control and so on. So this was a very interesting idea at the time. We developed a lot of ideas in network data fusion, network control, all these types of problems. And we talked a lot about things like network sensing and so on, and nobody was interested. You've got to remember this was back in 1990, all right? So I then dropped the whole idea. I came to Australia, and then by about 1995, 97, that sort of thing, people were saying, oh, network sensors, network-centric warfare, all these kinds of things. And it turned out a lot of the original algorithms that we developed for this kind of project, this one here, turned out to be extremely valuable. So I got back together again with a company that I'd worked a great deal with, BAE Systems, in the past, and they're basically, this is an interesting commercialization lesson, because unlike Patrick's or unlike Rio, they are not the end users of the technology. They're basically technology developers themselves, and they take that technology and sell it on to defense forces in the form of various products. And what they wanted in this case was a defense demonstration of all these network data fusion principles, network data fusion theories, and so on, both in the sense of how information's put together and how you get multiple things to cooperate and coordinate and so on. So in this case, it's very interesting because our role is no longer the direct commercialization route. Our role in this case is to demonstrate technology and get it inserted into a company as part of some global supply chain. It's a very different model from the sorts of things that we saw before. But again, this was a tremendously exciting project, and I often say at this point, if we had known how hard these projects were going to be, we would probably never have started. So this basically shows a demonstration of many UAVs all flying together. There's nothing on the ground in this case, no controllers on the ground. Okay. What happens is these aircraft are actually downloaded a potential target map of what's going on the ground. They then basically start talking to each other, and then on the basis of what they say to each other, and for the academically inclined here, they talk in terms of posterior probability distributions. Okay. They then decide which targets they're going to visit, which ones, how they're going to search, and so on. So all of these things, while they're in the air, you've got no idea what they're going to do. All right? So this is a really scary project. Make sure, I often say to my students, you've got to make sure the code works first time. All right? And indeed, we have lost more aircraft here. And the other thing that we developed in this process was to try and apply some pretty advanced machine learning algorithms as well, where you basically do things like fly over with a camera or drive past with a camera, and you want to be able to, for example, identify trees but not bushes. That's a pretty hard algorithm, okay? So what is it that makes a tree and a bush, and so on? What makes a tree look like this on the ground and look like this on the air, from the air? And how do you fuse that information together? But again, crucial technology for a lot of the sort of operations that people like BAE, and indeed now also in areas like mining, and we'll see a few other applications in a minute, want to actually apply this to. So it's had some really impressive outcomes, in fact. The Type 45 air defense system is now based on a DDF technology. The future UCAV, you'll notice that this is actually being demonstrated in Australia. You can see the red ground behind it, are all based, again, on the DDF type of technology. And also now in ground sensor networks, a whole variety of different applications. I think the important thing here is that maybe we don't commercialize it as a startup company or as some of the other things I've shown you, but it's been very important for us in Australia to be part of this global supply chain in which this technology gets integrated and so on and so forth. Some of the other spin-offs, which I think are interesting, is we've gone into using UAVs for agriculture. And this is spun out of basically exactly the defense things, uses the same algorithms, but instead of finding targets on the ground now, we find invasive weeds. Okay? Same types of machine learning algorithm, but now we can find things like prickly arcadias, we can find sylvania, lots of other very specific types of weeds in different environments. In dam areas, you can see this area here is a clogged up dam, and you'll see the spray booms on the side of the helicopter here. So it can go along, find the weeds one by one, and spray them one by one. Okay? So no more spraying over the whole area. This is, again, exactly a great application for this type of robotics technology in Australia. So the other areas that we've been trying to push into particularly are trying to use those same sort of machine learning concepts to apply it in more unstructured environments. So let's forget about mines and things like that, but instead try and get a vehicle to operate in bush areas. Now there may be many applications of this, although these particular videos here are particularly defense context. One could envisage many of these applications being, for example, in bush firefighting, in forestry, in terrestrial ecosystems and so on, where you actually use airborne platforms, ground-based platforms, build up a fairly complex model for what's going on, and actually use that model to control the outcomes of these platforms. So again, you want to do a lot more sophisticated processing now. So we've got long gone are the days of just using a radar or just using a radar. These images are actually generated from combined laser, radar, infrared, cameras, ultra-wideband radars, extremely rich models of the environment, and on the basis of that, being able to distinguish things like trees from bushes, from terrain, from cars, and you can even see a fence and various other things like that in there if you want to actually get these robots to operate in these complex environments. And ultimately, one of the goals is to take that and not just deal with data and show data, but to say that that data is a tree, that data is a car, that data is something else, a pedestrian, and so on. So actually interpret this information in terms of something that people or a machine can actually use in a visible form. Here's another interesting outcome, yet another startup company out of the group, and this is really quite a nice application. We actually had I'll explain what it is before we get there. These are sniper training robots, so they run around a training facility. All right, this training facility is in Western Australia, and people shoot them. Okay? And they're pretty clever robots because they got microphones on them. So when they get shot, they actually fall over and look like they're dead. But the other ones run away. All right? So it really makes it a very hard challenge. They go in and out of buildings using all the navigation technology that you've seen in previous projects. They've got all this cooperative control thing, so they know how to behave together. You could have one bad guy, 7 good guys, these sorts of things all running around. It was an interesting project because we actually had the generals in the lab and we said, okay, this is what we can do with robotics. What do you actually want? And what they didn't say, what they said was, well, we don't want them for combat. We'd like them for this application, and here are a few others, and so on. So again, this kind of engagement with the end user. And this company not only has now sold them in Australia, but it also, very unusually, has sold a big system to the US Marines. Selling defense technology into the US from Australia is a non-trivial thing to do. And as of last week, they also sold a system to the Jordanians as well. So this is a really interesting niche application of this kind of technology. So let's look at a few other applications. Again, one of the first things I did when I arrived in Sydney was start an underwater vehicle project. If you're coming to Australia, you've got to find some excuse for spending time on the beach, right? But it turns out also we have such a wonderful ecosystem, a huge exclusive economic zone around Australia, that really marine robotics is one of the few ways that you can actually hope to do stewardship, or you hope to do this monitoring and mapping, and indeed other potential commercial applications offshore. So we run this deep submersible. This is about a 1 kilometer depth vessel. It's untethered, but it's got many of the same technologies that I've already shown you. Different sensors, so it's got vision, it's got acoustics in this case rather than anything like radar, but the same type of thing. We want to build up maps, we want to use those maps to do navigation and so on and so forth. We want to build up data information, various other things that the end users of these sorts of things actually want to employ for various applications. So this actually is interesting here. So again, if I didn't show the video again, that robot running around in the corridors, one of the key technologies in that was how you build a map and then use the map to navigate when there's nothing like GPS, right? And SLAM is the technology that does that. It stands for simultaneous localization and mapping. And this is probably the reason that I actually got elected an FRS. Okay? It's been one of the most important contributions probably in robotics in the last decade. And in this case, underwater is another good application. There's no GPS, there's no maps, but what you can do is you can use your acoustic and your visual information. If you look carefully there are red dots and green circles. They're basically the raw information. You can use that information to basically start building up a map, and then as you come round with that map, you can actually do this matching between the different parts of the map, and on the basis of that, you can update the map and update where you are, and effectively continuously build an improved map and figure out where you are at the same time. All right? This really is an autonomy problem. To make a robot autonomous, you want to drop it in and just let it go. And this basically does exactly that. So this is core technology, and we're one of the only people who know how to apply this underwater in this case. It's fairly sophisticated, but nevertheless it's very valuable. And there's a big program, some of you may be aware, IMOS, in which now there's continual observations made all the way around Australia. And we do deployments every year. This is this year's deployments, Ningaloo Reef off Tasmania, and so on and so forth, doing these surveys. So this is the Ningaloo Reef survey. This is a survey off the Barrier Reef looking for what happened in the last time that the world warmed. All right, there are old coral reefs underneath the current coral reefs, and by exploring those and mapping those gives you some sense of what will happen in the future. Here's another very interesting one. This is done, in fact, in the Spencer Gulf off Adelaide, and it's again, turns out cuttlefish are good indicators of pollution. So we send the vehicle out all night, and what it does is it counts cuttlefish. And these are actually quite hard to find because, of course, cuttlefish camouflage themselves, and it is dark. All right, so you've got to use some quite sophisticated algorithms to find out what's going on. So let me just put one other thing here. One of the great things in our group is having a wide diversity of different people all involved. This is actually our media artist. We have a full-time artist who works in the group. This is actually a robot sculpture called Fish and Bird, and it's based on a Greek love poem about how fish and bird fall in love, but they can never be together because they're in different mediums. So this has been quite an interesting project because you've got two robot wheelchairs here. You walk into the environment, and then depending on what you do and what they do, they behave in very different manners. They behave towards you and so on. So these go on exhibit all over the world. We've got about 30,000 subject references now, and this is often the first time people have ever engaged with a robot in an interesting way. And so these robots navigate around depending on what's going on with everybody else, and then they write, you see these bits of paper on the ground, they write different love messages to each other. All right, isn't that nice? So I often ask myself kind of what we did right in this process, and I think there are two big things. The first thing was to come to Australia and focus on a technology for which probably the biggest user in the world is Australia. All right? That's been the biggest success. You look at all the applications I've shown you now, if you were to pick somewhere where you really wanted to apply it, it would be in Australia first. Mining, agriculture, marine systems. Okay, cargo handling's everywhere, but bear with me there, okay? So I think that's very important. The second thing is, with this kind of technology and with the way we engage with industry, is to attract really an amazing group of people. We've grown from 10 people when I was first in Sydney, you might even remember that, Matthew, to about 250 now across the whole group with 120 PhD students. We have to fight them off to come and work on the beaches, with the aircraft, even in mining these days. So it's been a really excellent exercise in really trying to encourage people to take on this kind of technology. So I'm going to stop there and just really say something about what I'm thinking about doing in the next 10 years. I think for us, mining technology is really the big driver. Because there's the investment going on, because there's the need for this type of technology and so on, there will be large investments in trying to make automation, trying to get the value out of automation in mining. And I think it's fair to say that the mining application at this point is probably pushing technology worldwide. There's more sophisticated data fusion, automation technology going on in mining than there is even in the defense field now. And I know because we collaborate a lot with the defense people. I think a second really important application is to take this technology and apply it to environment monitoring applications. I've shown you a number of marine applications, but there's a big interest in doing terrestrial ecosystems, really understanding and being able to steward our environments, getting those sort of data products. So it's not the robot again, it's the way of getting information out of the system and being able to use that in some useful process. And finally, I think there will be societal applications of these. And I think things like the art thing that I showed you earlier, a number of other elements that we're looking at, applications like remote assisted care, bush firefighting, these are really the applications, A, which are drivers in Australia, and B, which I think the technology is now ready and thriving to go with these. So I think I will stop there. Thank you very much.
Don Fry.
Hugh, what have you got planned to help Mr. Obama's oil leak in his Gulf?
That's a good question, and interestingly I've been asked that question at both of the previous talks that I've given. We actually have a guy from our lab in field in the Gulf of Mexico at this time, all right? And the reason for that actually is quite interesting. He specializes in using the robot that we have of mapping benthic plumes, that are plumes that are basically coming up from black smokers. And he's been mapping these for other reasons, actually to find the black smokers in the first place. But it turns out all the algorithms that basically sense that and build models of them and how they flow are exactly what they need for that sort of thing. So in fact, he left last week. He is currently in the Gulf of Mexico doing exactly that. Because I think a lot of the problems are with the dispersants in there, these big plumes are staying underneath the water.
Hi, Vincent Conrad from the NAS Group. You've got environmental monitoring out in your 10-year window, but you're already flying and swimming around identifying cuttlefish and different things. Why such a long time frame for that to be taken up?
Okay, let me rephrase that. I think it's interesting the way some of our processes work. You know, and maybe you can see it like in the agriculture example I showed you. We get people like defence to fund it, right, and build all the aircraft, and then the farmers who can't afford it can then also, you know, effectively utilise that technology. And to some degree, this is what's been going on in the other areas. The marine stuff, initially there was some defence funding and various other things which got us going. But now it's if you like it, because you're actually now working with biologists, working with people who actually, you know, need that product and can see what you can deliver, it becomes self-sustaining, okay? I think we still have that to go in the terrestrial ecosystem side of things, all right? So we're seeing agriculture applications, so all these different cooperatives. Every couple of weeks, my colleague Salah is off with the banana growers or the cotton plants or whatever else it is, looking at different types of weeds or different types of things. It's not long to think, okay, so now instead of just taking one robot, let's take a lot of smaller robots and actually do a bit more persistent monitoring of that, provide the data that people need to manage that whole process. And again, I had a very interesting talk in Brisbane because we had the cane farmers and various other people who clearly have been thinking along similar lines. Do you know what I mean?
They wanted to know if he could spot cane toads.
Yeah, and then shoot them with a laser. So I think, if you like, it requires the right time and the right people, and the terrestrial side is really beginning to come together. And I think that's very interesting. And when I look at the application in Australia as I fly out to the Pilbara, these huge areas, I mean, the only way of really understanding what's going on will be to use robots of some description, and that data fusion technology and so on. The marine side was an interesting lesson, because I think there was a user acceptance problem. Okay, because they wanted to, they thought that they could do it by dragging a sled, and they've always done it by dragging a sled. And what could you do that we can't do by dragging a sled? And then we produce these incredible images, and they can do science they've never done before. So you really got to go that extra mile and work with the user. Scientists are just as bad as industry in that sense, right? And equally with farmers, no one was going to pay for the first one, but the moment you can do those, find every single prickly pear and spray it in his yard, right? Then they begin to believe. And you need to do the same process throughout. So I think all of these things, you need to, you really need to get that community going, and you need to work very, very closely with that community and understand, what the process is. So I now know what all the invasive weeds are, but you're not credible unless you can do that.
Yeah, Chris Fraser from Minerals Council.
Yeah.
And so a mining-related question, and it's about skills and developing into the future with the automated mine. What are the types of skills that we will need to run these mines, and do we have those type of skills now, or are we going to be upskilling existing employees such as electricians and electrical engineers, or is there some other type of skill set that we don't even know about yet that we should be starting to talk to the universities about?
That's a very good question. I'll preface it by saying afterwards you might want to talk to Andy Stokes, who's at the back, who's our Rio guy, because, these are questions that they are grappling with themselves. I think it's been interesting, the drill process, how readily the drillers and the maintenance crews have actually adopted it. Do you know what I mean? Or admittedly, they have to have their hands held to start with, but there's a degree of enthusiasm. They're no longer sitting on a drill rig. They're sitting in a comfy cab, or indeed, in principle, they could sit in Perth. So their lives themselves are actually improved. And I think, there's a big plus to that. And we saw that also on the terminal, in truth, Patrick's got the thing right. They were going to pay the waterfront guys by how many boxes they move. And they discover, well, the automated ones move them quicker, and therefore if we work for the automated ones and help it work, we actually get paid more. Do you see what I mean? So there's a kind of process. So I think the skills are actually there for most of what's required, okay? It may need upskilling, but nevertheless they're there, and the enthusiasm's there as well, providing they're actually brought on site early and properly, and so on and so forth. At the other level, though, which is how this stuff gets developed and so on and so forth, yes, there need to be, you will need the electrical engineering graduates, the mechatronics graduates, and so on. But it's a different kind of graduate. It's a graduate, I've got to be honest, I have the advantage of being a Federation Fellow, and so I no longer teach, right? But there is an issue of actually getting our undergraduates to actually want to get out there and do real things rather than just theoretical things, to learn by doing, if you see what I mean. For us, at least at this point, that only happens at postgraduate level. Do you know what I mean? So it doesn't really happen at the undergraduate level, and universities are not really set up to do that. But at the postgraduate level, the guys who go out of here, who go into Patrick's or who go into Rio or whatever, these sorts of things, they're really people who can, frankly, you saw that picture at the end. They can go anywhere, do anything, automate whatever is needed in whatever environment. On the water, in the Pilbara, on the other side of the planet. And that's the kind of skill base that you actually need. And we are generating them, and there's a lot of enthusiasm for it. What can I say? There's going to need to be a lot more. And the universities themselves are going to have to change, in my belief.
Kevin Sanders from Levels Affairs, one of those growers.
Yep.
Just interested from our perspective, how close you are to being able to pick it up.
That's a hard problem. I mentioned having the generals come in to talk because, of course, one of my favourite cartoons is a picture of the staircase and a door at the top, and there's a Dalek sitting at the bottom, and it says, "Damn, there goes my plan to conquer the universe." All right? Because we can get robots to do a lot of great things, but getting a robot to climb stairs and open the door is basically never been done. Okay? You just cannot do it. And we once went out to Orange, with the horticultural people out there, and we watched the low-paid student pickers picking, and they can pick like grease lightning. There's no way you could get a robot to do what they do. I mean, it just is. I mean, you could get it to do it, but it just would never be effective. Do you know what I mean? Yeah, look, I've seen them as well, but you see how quickly a person can do it and how efficiently they understand whether that's ready to pick and whether the right thing and how they and everything else. The skill involved in that relative to the technology, relative to something else. I mean, this is sometimes my point is, so I can fly. We have a UAV. It went in South Australia, flew for 100 kilometres, spraying individually every weed. Okay, that's what you want to get a robot to do. Okay, do you see what I mean? So it's kind of finding what the right technology is at the right thing. We're not there in terms of agility, dexterity, other sorts of things. It's a hard thing to do.
Wayne Fitzsimmons, the PSC Foundation. Hugh, have you put your mind to thinking about intelligent transport systems and the application of robotics?
Yes, we have. We've avoided it too. And we avoid it, we have 3 rules, right? When we start a project. Is there good research? Okay. Is it good for Australia first? Okay. And the problem with transport is everyone else is doing it. Okay. So I can go to Germany and Mercedes and everyone else are doing it. Go to Japan and the US are doing it and everything else. So why should we do it? We have all the other things that we could be doing. Do you see what I mean? So it's not that we don't have technology that is valuable for that type of problem. Okay, or indeed, as someone who doesn't drive and has to use public transport, are not even concerned about the problem. It's just that there are so many other good opportunities in which Australia is the biggest and best market already, all right, that we choose to focus on those.
John McDonald, Design Inc. Architects. What about applications in space? I understand there are 450,000 bits of space junk floating around up there. I mean, could we collect that up with?
Again, actually, we do. Actually, we have some space programs. We get funding from NASA and people like that. But the problem with that is, you build one robot every 30 years, and you send it somewhere, and it's only one robot, and by the time it's there, it's 20 years out of date. I mean, do you see what I mean? And it's not actually that exciting, in truth, from a research point of view. I mean, I know it looks cool on the TV and stuff. Do you know what I mean? I mean, it's equally, we don't build humanoids. I mean, Japan builds a lot of humanoids, and I always find it interesting, their videos of mine automation often involve, with the exception of Komatsu, because I know there's someone involve a humanoid sitting in a cab. Do you know what I mean? So that is one way to automate a cab, a thing. Do you see what I mean? So I guess we've chosen things which we feel are going to have an impact in Australia. It's been a very important focus for us. Because that's the way, I mean, that's what. And again, if I can extrapolate, this is why Japan works on humanoids. They're worried about aged care. That's their major driver. Or why the Europeans work on manufacturing and transport, because that's their big driver. And why the Americans just build unmanned drones and things like that, because defense is their main focus. Do you see what I mean? So we've got our niche, and it turns out to be a good niche.
Jamie Ross from miningman.com. So another mining question. Mm-hmm. Underground mining versus surface, obviously no GPS, but much more defined pathways. Yep. Are there insurmountable challenges underground?
No, in fact, I'd go even further. The underground automation problem, to a large degree, things like LHDs and trucks, is solved. The technology was there 10, at least, if not 15 years ago. The reason it has not been successful is that people have forgot that we didn't want an automated X or an automated Y. We need an automated mine. And that requires thinking when you're building it, how am I going to build an automated mine with everything integrated, the picture, the data fusion, the information, et cetera, and then I'll get the people out of the cabs. That's why it's not worked. And it's been interesting. So many people have tried it, and the technology, it's not the technology that's failed, it's the implementation that's failed. And I think that's a big, lesson that we have all, well, at least I think I have learned it.